Morning, everyone. What I'd like to present to you today is the results of a study that we've been doing in the Maputo coastal plain. The study, it's a multidisciplinary study. Guy Bates, I see guys here today. Ricky Taylor and myself have been looking at the KwaZulu-Natal area in particular. The main focus of this particular project was to try and link hydrological, biological and ecological drivers. And what I would like to present to you today is actually the hydrological side of some of the results that have come out of this particular study. Ricky's going to present some of the ecological ones after this, but I'm just going to focus on the hydrology. Now this is the focus area that we were looking at. The water resources here, surface water resources here, comprise perennial streams that feed into Lake Shazibi, Lake KwaZulu-Natal, and that drains out into the KwaZulu-Natal catchment there. One thing you should all realize that these streams, some of them as far as I know never stop flowing, and they are minute compared to the major rivers in the country. So you immediately can understand that there's a major difference between the functioning of these particular systems. Now from a hydrological perspective, this area here, these water resources sit in a coastal environment with very deep soils. Some of them are over 100 meters deep, highly permeable. So this system is actually driven by groundwater. So when we want to analyze it, we've got to move away from the concept of a hill slope type process to one that is groundwater dominated. Sorry, technology running away from me. So from a hydrological point of view, instead of the little focus area that we were looking at as this multidisciplinary project, if we were to use the traditional form of hill slope type hydrological processes, we would start to use the traditional topographical catchment area. And the black lines here represent what would have been a typical topographically defined catchment. But with a groundwater dominated system, we have to realize that it's the groundwater that is actually controlling the systems, and we need to look at the groundwater catchment area or the recharge area for this particular system. And you'll see there I've drawn a couple of lines, a couple of polygons that represent the groundwater area that contributes to the lake system. This catchment area, the groundwater catchment area, is based not on topographical ridges but on the groundwater ridges. So when you have rainfall impinging on the groundwater, it will flow down these ridges into the drainage lines. So you can see there it's substantially different in terms of the area that represent the catchment area for this particular system. And this is common for the whole of Zululand, where the system, where the hydrology is driven more by groundwater than it is by surface water. And because we're looking at the groundwater ridges to define these catchment areas, we don't have that sort of data that's available. We would need an incredible array of boreholes to be able to map it. So I've had to resort to groundwater modeling. And what it is those ridges now are determined by the drainage boundaries. And the drainage boundaries that I've selected here in terms of this particular catchment are the ocean, which is fixed sea level here. We have up in the north there, Lake Sabai, we have water level measurements. Sabai has been declining fairly dramatically over the last few decades. On the west there we have the Mbazwan River that drains to the west of this particular area. That feeds down into the Mpuzi rivers and into St. Lucia. And down in the south we have a fairly static water level, Lake Bongazi North. It's got an outlet to the sea, so we know that the level of the water lake down there stays fairly constant. The other thing you'll notice is I've got more than one line representing the groundwater catchment area. And that is because the groundwater ridge is dynamic. It moves under dry conditions, under wet conditions, so it is never static. And this is taken, those particular ones are taken from a wet period and from a dry period, and the one in the middle represents the average sort of catchment area. So it's a very different environment to the one that you would typically pick up using the standard hydrological processes. Pressing the wrong button there. Okay, so I've had to use a model to be able to predict this water table profile in order to determine the catchment area. And I've selected a model from the United States Geological Survey called ModFlow. It models the whole of the groundwater dynamics. So you have recharge coming in, and then the groundwater is diverted to drainage lines. And the model is linked to a surface catchment model that simulates infiltration, percolation, and evaporation. So I'm able to take into account the impacts of land use as well. The model also is dependent on the geology. So we have, fortunately, we had Water Affairs come in and drill a whole lot of boreholes for us at 8 sites. So we have a very nice stratigraphy of the aquifers there. We had a master student come in and do a geophysical survey, and as we were able to capture or calculate the hydraulic properties of these particular aquifers. So we've been able to get some information on the settings for this model. We have very little other information. There's no stream flow measurements being taken in the area before this. We do have water level measurements at Mbazwan. There's a forest, there's a borehole there next to the forest, and it goes back for, I think, 20 odd years. We had another borehole down near Sidwana, down here, where we have another 15 years of water level measurement. And we have rainfall measurements from both those stations. Other than that, we have very little information on this whole thing to be able to estimate what hydrology is actually doing. The other thing is that we've got land use, which plays a very big role in the groundwater hydrology. And we've got 2 important features here. We've got the natural grasslands. And on top of this, we have got these major plantations that have come up. That's in Mbazwan State Forest. And the little greener patches down the bottom there are these new woodlots that are springing up everywhere with eucalyptus trees. So those are having a fairly big impact, as I'll show you just now, on the whole of the hydrology of the system here. So using this particular model, or setting up this particular model, because we don't have all the parameters, we have to go and do a bit of calibration on these things. And the one thing you do is you calibrate your storage, your water level elevation, and that shows you a graph there now of measured water levels against the predicted water levels over the entire catchment for a 10-year period. So I forgot to mention, this model starts under average conditions and then runs for a 10-year period. The Mbazwan borehole is this one up there. Further down the bottom there, you see the Sidwana one. So we are getting a fairly good relationship between predicted and measured values in terms of the groundwater storage. And this here shows you a graph of the actual time variation in the water levels at those 2 sites, at the Mbazwan. On the left there, the red is the measured values, and the blue is the predicted trend coming from the groundwater there. And you can see that the predicted one isn't quite as big a drawdown as the actual measured one, but I think it shows you the same trend. This one at Sidwana here shows you a fairly much bigger variation in the water levels, the predicted water levels, but it still follows the same trend. So we feel that the groundwater modelling of this thing is actually fairly sound. The thing that we need to be sure of, though, is the recharge. This is something that is generally ignored in groundwater modelling in this country. So very few people try and calibrate the recharge component to a groundwater model. And what I've assumed here now is that what comes in must equal what goes out in a mass balance type situation. And to do that, the surface conditions, the infiltration, evaporation components need to be calibrated to such an extent that what is predicted flowing out of the system matches what can be measured. As I said, there were no flow measurements when we started this project, so we've got students in there, cheap labour, to start measuring water levels, or not water levels, but flows at these particular sites throughout the area there. And this is a typical type of stream. Well, that's a canalized stream next to Bekapanda camp there. The one on the left is a road crossing at the northern top up there, Tolisakhat. That particular one, as far as we know, has never stopped flowing. Some of the people say that it's linked actually in elevation to what happens in the estuary, but I think that we have actually managed to show it's not quite correct, but it never stops flowing. The flow actually at Shazibi Culvert down here, that actually dried up at the end of 2015. So we are seeing a problem here now because it's flowing very strongly up the Tolisakhat and it's through Lake Sevi, and it's not getting out into the culvert into the estuary there. So we feel that there is a loss a transmission loss somewhere along that area there. And the model actually shows it to some extent, I'll show you now, but it is an area that still needs quite a bit of research. But in terms of the calibration, the bottom graph there shows you two of the predicted stream flow measurements. At Tolisakat and at this Shazibi culvert. And these values here represent the measured flows at that time. So we know we have got the flow measurements relative, the simulated ones relatively close to what is actually measured there. So based on these calibrations, we feel the model is good enough to start looking at some of the hydrological processes and looking at some of the potential impacts. So I just want to show you very briefly here some of the flow dynamics that come out of this particular model, and then look at some of the impacts that the model has predicted on the area there. I mentioned the catchment area is determined by the groundwater ridges. The black lines there represent contours of the water level elevation throughout the area there. You'll notice that they all come and are these areas here where the contours curve indicate it's a draining stream. So you can see in Buzwan up to a certain point is actually draining at this particular time. I've forgotten what this particular time was in terms of representation here. Remember, this is a 10-year sequence of values, and these contours change. And the grey arrows in there are velocity vectors. And you can see they indicate clearly where the water diverges along the ridges there and goes down into our catchment area or is moved from it. So the model is able to show us exactly where the water is flowing and approximately at what rate. This is in the surface elevation. We've got similar maps at the different depths. The model was configured as 3 layers representing 3 stratigraphic units, so we can represent the same thing at any particular level. We do find that there isn't a lot of vertical mixing. You do find water going down in elevation, particularly in the top surface, but you also find some water rising in the lower elevations as well. I haven't got a map of that here, but that actually happens in the vertical. With this type of information here now, we know where the water is coming from, we know the rate and velocity it is, we can calculate the distribution in the actual rivers themselves. We can also do a full mass balance of the water in the lakes. And so this is information that is generated through this groundwater model. The other thing that we can do is start to look, using this model, to trace possible contaminants. And I identified there on Google Earth the possible location of all the settlements. On the left map there, all those black spots are potential settlements there that have grown up, I think, over the last 20, 30 years. And I put a hypothetical particle there, solid particle there, and I asked them where this thing would end up after 10 years from the model. And the red lines here will show you where that particle has actually got to after that 10-year period. You can see here, the groundwater catchment flows through here, so all of these here are flowing and they're captured by these rivers into all these ones here are flowing down towards Lake Shazibi, but you'll notice here that there's some are actually going underneath the river. So we think, at least my feeling is that this has become a losing stream. So it's not picking up the flow that's coming out of here. Everything north of that is flowing out to sea. All the development down here is going out to sea. So we are picking up patches here that are potential areas that can contaminate this area here. So it gives us an idea of where the stuff is coming from and where it's likely to be going to. Now remember, that's a 10-year trace. If you wanted to find out the total time that it takes to get to any particular place, we'd have to extend the simulation period. The other thing that everyone feels is the groundwater extraction from boreholes in the area there is having a major impact on the groundwater. The model I put in there, Guy captured the position of all the known boreholes there for the lodges and the private residences all around Sodwana. And I put those into the model, and I assume what would be considered as normal household use for water as the abstraction rate. And I can find, the model is not able to detect a significant change in the groundwater contribution from these abstraction points. And to verify this, we put loggers in here. This is Lake Shazibi. We had a logger in the wetland here, and this is, red is the trace from that. Ricky put loggers in this lake here. We lost one to vandalism, and we put another one in. And that is the blue line here. And the green line is a borehole in Sodwana Bay wellfield. They have 5 boreholes there. They pump to supply the lodge. And if you look carefully here now, the borehole follows very similar trends to the lake. There's a little bit more variability, but I cannot detect the drawdown from the abstraction in those boreholes there. So if we want to be able to show that there has been a significant impact, we need to do a lot more work on that particular thing. As I say, I'm battling to detect exactly what the impact is. Okay. Now, on the other hand, the model was developed and simulated under current conditions, which is the plantations, the state forest, and all the woodlots that have been developed there. And this is the state forest, the orange. These are all the woodlots that are popping up south of there, and all up here. And what I wanted to do now is I ran that. I then replaced the plantations with grasslands, and I subtracted the two to see what the impact on the groundwater was. And those contours there show you the drawdown associated with the plantations. And in the middle of the plantations here, we are picking up a drawdown of over 9 meters. Now, if you take the Mbazwan borehole, and this is the measured value, the blue is the predicted, that's the trend. It works out at about 11 millimeters per day. This is for the grassland, with a drawdown or with a drop in water level of about 3 millimeters a day. This we're attributing to drought. So this is over and above the impact of drought. So the loss of water there, the drop in water level, cannot be attributed to drought. This impact extends further down into the rivers. This is the flow in the Shazibi, flow into the Lake Shazibi. This is under current conditions. This is under predicted grassland conditions. We're getting a halving of the flow into Lake Shazibi according to the model. And finally, one of the things I've looked at is a geomorphic setting for the formation of wetlands. We did some work at Kosi to Tembe, and we found that the model was able, using the depth to the water table, able to predict the geomorphic conditions for the suitable development of wetlands. The one on the left there is the distribution of the right geomorphic conditions for wetlands. You can see they're all around the lakes there, which we know are swamp forests. Down the south there, towards Songweni and the Mbazwan stream, we're picking up the ideal conditions for wetlands. This is a situation under grassland conditions. So it appears that we have lost the right conditions for wetlands all throughout the forest there and even down a bit to the south there. Thank you. In summary then, the model is able to provide some idea of the hydrodynamics of the system, describe some of the sources or potential sinks for or potential contamination sources, and estimate some of the relative impacts from anthropogenic effects. The model, however, is not able to look at the estuary itself because that is governed by the mouth conditions as opposed to the hydrology. Thank you. I just want to acknowledge everyone that has been part of this particular project.